Today we're going to look at inverse functions. So let's start with this opener. And after you process this, hit pause and try and work it out yourself and then see how you did. So we have two functions. F of x is 2x minus 1 and g of x is x plus 1 all over 2. Find f of g of x and then find g of f of x. And notice I just used the two different notations for composition. So just to show you and remind you that there's two different notations. But first do f of g and then do g of f. Okay, I'm going to work through the solution, so hopefully you have paused and worked it out yourself. So for f of g of x, I'm going to send f the g function. So I'm going to put x plus 1 over 2 into the f function. And so that's going to do 2 times the input minus 1. And these 2's cancel. 2 divided by 2 is 1. So we're left with x plus 1 minus 1, which is just x. Okay, now let's do g of f of x. So I'm going to send f to g. So I'm going to send 2x minus 1 into the g function for x. So I'm going to put 2x minus 1, and then I have plus 1 over 2. Well, as you can see, the 1's cancel, that's 0, and then 2x divided by 2 is just 1x. So we get g of f of x equals x. So in both cases, the composition wound up giving us the identity function. And that tells us something about these two functions. And it tells us that they are inverses of each other. So here's a formal definition for you. If f and g are two functions, and f of g of x equals x, and g of f of x equals x, for every x in the domain of each of those, then we say g is the inverse function of f, and we can actually say vice versa, f is the inverse function of g, and we denote g by f, and then it's a little negative 1. Do not think that that means 1 over f. Okay, so that's not like f to the negative first power. That's the notation for an inverse. So if we're dealing with a function and you see that negative 1 power, just remember that that means the inverse of the function, not 1 over the function. Now this is really important that when we start getting into details, the domain of f must be equal to the range of f inverse. And the range of f must be equal to the domain of f inverse. So they're switching domains and ranges. So the notation, we could say that f inverse is equal to g, or we could say g inverse is equal to f. Let's look at some different representations for this. Let's say that we have a mapping. And this mapping shows a function because there's no input that goes to more than one output. And what if I wanted to find the inverse of this function? Well, I just so happen to have an easy button. And to find the inverse, we're just going to switch the inputs and the outputs. Or in other words, just switch the arrows on our mappings. So it's going to go back. So instead of, for example, 5 being matched to 9, now 9 gets matched to 5. So that's easy to do when it's a mapping. What if we have a set of ordered pairs? What would be the inverse for this? Well, we're just going to switch all the inputs with all the outputs. So for example, if I pick here, if negative 3 outputted a negative 7, for the inverse, a negative 7 now will be the input, and negative 3 becomes the output. So we're just switching our inputs with our outputs. And it's as simple as that. So mappings are easy, ordered pairs are easy. What else do we have? How about algebraically? Now, to figure out the inverse algebraically, the first thing we need to do is rewrite your function as just y equal. So I'm going to say y equals 2x minus 1. And then by switching inputs and outputs, that means we're going to make all the x's our y's and all the y's become x's. So in your equation, wherever you see a y, write an x. And wherever you see an x, write a y. And now let's solve for y. So I'll put a little note here, switch x's and y. There should only be one y if it's a function. And then we're going to solve for y. And so when I solve this for y, I'll add 1 to both sides, and then I'll divide by 2. And that's going to be my inverse function. So f inverse of x is going to be x plus 1 divided by 2. If you think in words what this function does, it takes the input and it multiplies it by 2 and then subtracts 1. So the opposite of that would be to add 1 first and then divide by 2. So we're doing the reverse operations in opposite order, in reverse order. Opposite operations in reverse order. What about graphically? So we've done it as a mapping. We've looked at it as a set of ordered pairs. We've done it as an algebraic equation. What about a mapping? And by the way, a table would be just like ordered pairs. So let's say we have this function f here. And I want to find out what the inverse looks like. Well, when I switch x's and y's, let me make a point here. How about a blue point? When I switch x's and y's, I'm really reflecting every point over the line y equal x. So for example, and if I reflect this line over y equal x, if I can do this correctly, that's going to be my inverse. So if, for example, let's say I had the point, I don't know, 3, 5, for the inverse, it's going to become 5, 3. Okay. If I had negative 1, negative 4, now it's going to become negative 4, negative 1. And so we're just going to switch all the x's and y's or reflect it over the line y equal x. All right, let's look at some examples. And the most difficult ones are to solve algebraically. So that's what we're going to focus on. So if h of x is 8x to the third plus 2, find h inverse. So step 1, let's write it as y equal. Step 2, switch all the x's and y's. And step 3, solve for y. So I'm going to have 8y to the third equals x minus 2. I'm going to divide by 8. And now I need to undo the cube, or raising to the third power. So I'm going to take the cube root of both sides. And so I get y is equal to the cube root of x minus 2 over 8. And just like simplifying radicals, we can simplify the cube root of 8. So I can write my final answer, h inverse, I should write more formally, h inverse of x is going to equal the cube root of x minus 2, and then outside of the cube root is going to be 8, is 2, because the cube root of 8 is 2. So that's your most simplified answer. How about finding the inverse of this one? And now we start to get into the questions about domains and range. Find the inverse of that. So step 1, change it to y equal. Step 2, switch all the x's and y's. Now I need to solve for y. So first I'm going to have to square both sides. But see, by squaring both sides, now we've introduced new possible values. And then solve for y. So I'm going to have y equals x squared minus 1 divided by 3. Okay, so that's a parabola. Now the original graph, 3x plus 1, is just shifting. Well, it's going to look something like that. And notice we don't have the other part of this parabola, because we're just taking the positive root. And so when I reflect this over the y equal x line, I'm getting a parabola which has both sides, and we don't want both sides. So we're going to have to talk about what our domain restrictions are on this. So looking at the original, you know that 3x plus 1 has to be greater than or equal to 0. So that means that x is going to have to be greater than or equal to 1/3. So we have to tie that restriction to our answer. Well, let's look at the graph of this. Y is equal to the square root of 3x plus 1. Let's try that again. Okay. Oh, I should have shifted over a third, not one full unit. Anyhow, so there's our picture. So now let's go ahead and graph our inverse, which we came up with as, move this over here, x squared minus 1 over 3, so parenthesis, and notice we only want the point where, I should have written this as x is greater than or equal to negative 1/3. So I'm going to go to y equal, and I should say, I could get fancy here. I think if well, it'll do it on the axis, but that's okay. I'll say in parentheses x, let's go to my test menu, number 4, negative 1 divided by 3. So ignore where it traced along the negative x-axis, but basically we only want half that parabola. And that's the reflection of the blue graph over the line y equal x to get the red graph. So for our inverse, we have to make sure that we specify our particular values. And I'm sorry if I subtracted one, it should be negative 1/3. So we have restrictions, and you have to keep that in mind when you're doing inverses. Now, another thing that'll help with figuring out the inverses. The inverse of a function is going to be a function itself only if our original function is 1-to-1. What do I mean by that? Well, a function is 1-to-1 if it passes the horizontal line test. So we know to test for a function, it has to pass the vertical line test. So now we're considering, is the inverse of a function going to be a function itself? And so if the original function passes the horizontal line test, then when we reflect everything over y equal x, that horizontal or that vertical line test becomes a horizontal line test. I'll show you what I mean. If we look at y equal x squared, the inverse would be x equals y squared. Let's take a look at these graphs. On the left, you can see the graph y equal x squared in green here. And that's a function because it passes the horizontal line test. Any horizontal line, it passes the vertical line test because a vertical line doesn't intersect this in more than one spot. Now, it has a problem passing the horizontal line test because a horizontal line is going to hit this parabola in 2 points, except for when it goes through the vertex. And because the horizontal line hits it in 2 points, then when we reflect this parabola over the line y equal x, and we get this sideways parabola, now this sideways parabola is not going to pass the vertical line test because the original didn't pass the horizontal line test. So that's a way when you're looking at a graph, if the original function doesn't pass the horizontal line test, its inverse doesn't pass the vertical line test, and therefore its inverse is not a function. Let's say we have this function here, and you just see a table of 5 sets of ordered pairs there, 5 ordered pairs. So is the inverse going to be a function? Well, let's write out what the inverse is going to be. So we're going to switch all the x's and y's. So now we have 5 comma negative 3. Trying to be color coordinated here. And then we have, instead of 1, 0, Now we have 0, 1. And then instead of, well, let's do this. All right, and then we're going to have -3 in this spot, 2 here, 0 here. And then the inputs become outputs. We have a 0 here, a 1/2 here, and a 4 here. So all I did was change all my inputs to outputs and outputs to inputs. Now, is this inverse a function? Well, it's a function if there's no input that goes to more than one output. So 5 only goes to -3, that's fine. Here, 0 goes to 1, but down here, 0 also gets matched to 4. So now I have 0 being matched to 2 different values, and so that's not a function. Let's look at this. F of x is equal to 5x plus 3. Find f inverse of -2. Well, there's 2 ways to approach this. So the first way is, let's go ahead and just algebraically find the inverse. So I'm going to switch x and y and solve for y. So I get y is equal to x minus 3 over 5. And now, so that's my f inverse. And so now, f inverse of -2, I'll just plug in -2 for x. And I get -5 over 5, which is -1. Now here's another way to think about it. I'm looking for f inverse of -2. That means I'm looking for the original function's input that outputs a -2. This is for my original function f. So I can just say 5x plus 3. When does that equal -2? Subtract the 3. Divide by 5. Oh, when that x is -1. So that's the value that goes in here. So I know the point -1, -2 was on my original function, which means -2, -1 is going to be a point on the inverse function. So whichever way makes more sense to you, you go with that. Here's one last example. Find f of f inverse of 7. Now a lot of times this confuses students because they say, well, wait a minute. If we're using the same function here, 5x plus 3, so I'm going to do f of x is equal to 5x plus 3. So I calculate the inverse function, which we already did, x minus 3 over 5. And then I'm going to calculate f of f inverse, so I'm going to send x minus 3 over 5 into f, and that's going to give me 5 times x minus 3 over 5 plus 3. And when I simplify, those 5's cancel, and then -3 plus 3 is 0, and so I just get x. So wait a minute. So if f of f inverse of 7 is just going to give me 7. It's the identity function. But we should have already realized that, because if I take, let's say, if I take a point, let's take the point 1 comma 8 is part of my, is on my function f of x. The point -1, 8 is on there. So that means that the inverse has 8 comma 1. So this is f, this is on f inverse. So when I say do f of f inverse of a number, like 8, f inverse of 8 just gives me the original input, and then I'm going to do f of that input, which is going to go back and give me the output again. So it's kind of redundant, and I'm just going in circles here. So as long as f inverse is a function, f of f inverse of anything is just going to be itself, because it's the identity function. All right, so here's the problem set, and then when you finish, go ahead and submit those.